Hello and welcome to Super Simple Scala, episode 6. Today we talk about the Scala type system. The Scala type system is pretty cool. It's a little bit more complicated than the Java type system, but you can do some cool stuff with it that you couldn't do in other languages. One thing to keep in mind is that types are kind of like values. They can be treated like values, and they can be given a path. So for example, if I had something like, let's say object foo, and then object bar, and then type baz equals int. For example, if I had foo bar and then baz, I could say something like type, my int equals foo dot bar dot baz. And then if you could say something like val 5 equals 5, and my int is actually just the same as int. So you could actually just do 5, instead of doing 5 of type int, you could do 5 of type my int, or maybe even 5 of type foo bar baz. And then if you println 5, you're going to get, let's just run it. You're going to get, running main, you're going to get 5. Okay, so types can be assigned to variables. Types have a path. Paths can be sort of projected paths or concrete paths. This path is concrete because foo is a concrete object. You've instantiated it. Bar is a concrete thing. You've instantiated it. And this type is like a value that's inside of something that's been instantiated. If instead of this being an object, if this was a trait, like an interface, then look, this is red. You cannot resolve it because it's an interface. But then, how do we get to it? What if instead of dot we tried something like that, hashbang, right? So we went from foo to bar directly, and then to get from bar to baz, because we haven't actually instantiated an instance of baz, we use a projection, which says get something that's like inside of the trait, that's not inside of a real object. So this should also run and also give us the same 5, right? There's this notion, and let's go on to the other part. This part came right out of the book Programming in Scala. But basically it shows how types have their own independent paths. So if I were to get rid of this little example that was up here, now we just have this. Let's say there's a class outer, a class inner. We create a new inner. If you look at the type of this inner, it's actually outer. It's actually outer dot this dot inner. So this new inner is actually outer dot this dot inner, and this is actually of type outer dot this dot inner. That's really ugly, but just so you understand, the type kind of follows this path, right? So then we created an outer one, that's a new outer, that's fine. This is a new instance of that outer class. Then let's say we have outer 2 equals new outer, and then we override val inner with new inner, where this inner is actually not the same as this inner. Because if you look at the code, if we go to the build.sbt file and we set the xprint type or command line option, what ends up happening is if you do, one second, if you were to compile this, compile, and you were to take a look at what came out when it was compiled, you would see that, so we have main, we have class outer, initializer, class inner, private val this inner, private to this val. You can actually insert that here too, just to make that a little bit more clear. This just makes it private. It can't be accessed outside of this scope, the scope of this variable, which is in here. Private to this val inner equals that. Outer 1 equals new outer. Outer 2 equals, outer 2 of type outer equals, there's a final class anon that extends outer. That is an anonymous inner function, anonymous inner class. So we've created an anonymous inner class whose name is $anon that extends outer. Then we define inner. In it, we define our initializer inner. Don't need to worry about it, just call super inner. Then we have a private this val inner of type this inner equals new anon this inner, right? So what's going on here? The type of this inner isn't that outer and that inner. It's actually anon this inner. So it's actually this outer class here has its own sort of, it has its own this pointer. It has its own that, and that refers to its inner. And so this is of type this dot inner. And this is a new inner, a new this dot inner, where, one second, val inner overrides nothing, is a new anon this inner. What's going on? What's going on? One second. Something is being weird. Why is this being weird? Sorry, one second. Let's go back to the way it was before it got all weird. Oh, what if we got rid of this private this here? Oh, I see what's going on. So this is a private this, and that is also a private this. So this override here is the same as if there was no override. So if you look at here, it's just private this val inner. So that override is actually equivalent to that. So this is of type this dot inner, where this refers to the inner of, it's kind of confusing. But you can think of it as sort of the overrides actually turn into private this, and that also turns into private this. And this is of type this dot inner. There we go. That's of type this dot inner. And then this should also be of type this dot inner. There we go. So what ended up happening was that our original override val inner equals new inner got kind of turned into that. Okay. This should still compile, right? Yeah. And it should still produce the same, basically the same output as it did before. Okay. So with that in mind, what do you think will happen if we do something like, let's make it the way it was, back to the way it was originally. So this was override val inner, and this private was just this private wasn't really here. Instead, this private was just val inner. All right. So what do you think will happen if we did something like val outer 3 equals new outer, override val inner equals inner 1, outer 1 dot inner, right? So what if we got this inner, or yeah, what if we got maybe this inner, the inner from this outer, and we gave it to this inner? What'll happen? Well, it turns out that these things have different types in Scala. The type is dependent on the path a little bit. So this inner, this outer one here, the inner inside of this outer one is relative to that. The inner class is relative to what's inside of it. Whereas the type of this inner is relative to this, right? So this type is relative to this, and this type is relative to that, or you would say maybe this type is relative to, one second, let's do this one at a time instead of trying both at the same time. Compile, there we go. Yeah, so this doesn't compile. Overriding value inner in class outer of type this dot of inner dot this. Value inner has incompatible type. Override val inner equals outer 1 dot inner, not legal. Whoa. Right. So if we were to try it with the other one, same thing. What's happening is that this inner, the inner in this is this dot inner, is relative to that outer, whereas outer 2 is this dot inner is relative to a different outer. So the path that the type is taking is different, right? You can think of the path as like the type has a path. It has like you can think of it almost like directories. Like if you'd say like you can have two files that are in the same name, but if they're in a different chain of directories, they're two different files. In addition, things like a singleton, an object is a singleton in Scala. Object, my singleton equals, I don't know, it doesn't have an equal sign. Okay, we can have an object called my singleton. You would say, oh, that singleton, it's just a singleton. It doesn't extend anything. It doesn't have a type. Not true. Type singleton type equals my singleton dot type. And then if you had a function like def, take in singleton, I don't know, singleton of type my singleton type, and it doesn't actually have to do anything. But basically, this function, my singleton, so there's only one object on Earth that has type my singleton.type, and it's this one singleton. So you can call take in singleton on my singleton, and it's legal, because the types match up. This my singleton is of type my singleton.type. Right, so you can pass in something of my singleton.type, but if you were to have, my singleton, and then you had, object another singleton, if you try to call take in singleton of another singleton, what's going to happen? Type mismatch, right? I was expecting my singleton.type, the actual is another singleton.type, right? So every singleton, each object, you can honestly just say, int I equals 5. Sorry. Went back to Java for a second. Val I of type int equals 5. Type I type equals I dot type. Right? And let's do another one. Take in singleton 2. Right? S of I type. Wow. It's called taken singleton 2 on 5. Doesn't work. Doesn't work. The type belongs to the reference. If we were to compile this without it, oops, one error found. What is this, line 22? Oops, okay, that doesn't work, sorry. Anyway, so you've got this notion of, types being assigned to values, to these things. You've got this notion that types are sort of the types of inner classes and instances of inner classes are relative to the path of their outer class. You've got, notion that, a type can be concrete, it can be inside of an object, or it can be abstract, projected, it can be inside of like an interface or a trait in Scala. Types can be passed from parameter to parameter. So for example, let's just say, I don't know, let's say this singleton up here, my singleton had a type, had something like type, my type equals my singleton dot type, and this taken singleton function thing takes in a singleton. What this can actually do is instead of returning unit, it can return singleton dot my type, where singleton dot my type is the type of the singleton, and then you return the singleton, and what happens, the type is passed into the parameter and it comes out the return value. So you can pass types in and out, and instead of getting a subtype or a interface or something like that, you get the actual concrete type of that thing. And by doing this, you can actually pass types. You can pass the concrete subtype of a particular object from input to output, and that allows you to. You're carrying the types, and it also kind of allows you to do this thing where you don't lose type information, which is used in combination with implicit parameters to do cool things in other libraries like Shapeless. Infix types, higher kinded types. We talked about higher kinded types last time. We had a higher kinded type like type f of something equals like list. Type int list equals t on int. What's happening is list is a type constructor, int is a concrete type. You apply the concrete type to the type constructor. What ends up happening is you get list of int, which is a concrete type. And you can assign this type constructor to a variable, in this case t. Just out of curiosity, if we had something like t2 equals list, int list2, that can also work, I guess. If we look at the types of each of these things, t of int, all right. What else? Higher kinded types. If we look at, we're almost there. There's also this notion of these things called recursive types, where you can have, we can start getting into the fancy schmancy stuff right now. But let's say there's some fancy schmancy stuff in here. Woo! Crazy types going on right over here. What on earth is this? We have a type. append with something that takes in something that is a subtype of, this means like either less than or equal to on the type hierarchy of HList, and that thing in and of itself is a subtype of that. And then these things can be recursive. So here, this is our type projection, remember? So we're saying that this append is inside of an interface or a trait. So T here extends HList. So HList, and then T is a type that extends HList. So it meets this interface. And here, when we're saying T hashtag append, we're referring to the append inside of here. And then we're saying, pass in L, where L is a subtype of HList, and this here lines up to that. Really fancy things can be done with the type system. We're just going to try to make something readable out of it. Right, so we have our type projections. We've got, this append here is this append, which refers to that append, rather than, superclasses append. This is called Shapely, by the way. You can Google it and get the source code. Don't need to worry too much about that. Don't worry about macros. When we say 0.type, this is referring to the type of this. So this type n, it says this type n refers to the type of the enclosing object. And the reason we would have this this dot type here is so that we can sort of do the dependent method thing, where we pass in an object and then the return type is the type of whatever we passed in. This allows us to carry our type information from input to output. This here just is probably the exact same function as that. Type n equals successor of n, where n extends that. So pretty much the same thing. We went back to here. So that's that. So this type is, we've got this notion of that this type is the same as this type. This type is the same as this type. The parent is that, where we just say, the variable has to be of some type that extends that. In our concrete types here, this is that type. And since this extends that, this also has to extend that. This here is the same type as this. So if this extends that, then that also has to extend that. I mean, if this extends that, which means that this also has to extend that. So this extends, it gets confusing, right? Each of these things here, so if you look at, every single one of these, what ends up happening over and over again is you end up with type information that's being put into, for something like Shapeless, which lets you do some dependent types inside of Scala, or type, making constraints with types and things of that nature. What having these type values inside of your objects does oftentimes is it allows you to use that as a reference to pass type information down the chain. So the list extends HList, out extends HList. So whatever's coming out of the list is going to be extend HList. Let me see. Confusing. We've got our old friend implicit parameters. Remember, this just tells the compiler to grab the variable and put it in space. We've got some crazy stuff going on, but same old. Oh, recursive types, right? So I mentioned a type can be recursive. So in this case, we can have some type that extends the parent's type. Why would you have a type that extends itself? And the reason you would have that is so that when you override that type in the subclasses can return the most concrete possible type. So in this case, the type hcons head tail hashtag append list or whatever. So this type here refers to that type there, I believe. But what this type ends up being is it ends up being the most concrete possible type. So by using this recursive, some type extends itself, when you override it in the subclasses, instead of providing the parent's type, they get to provide the child type. You're probably totally lost, but so if we were to make this a lot simpler, right? Let's take this and let's go, oopsies. Let's go to Refine Types episode 1, right? Okay. So I'm losing my audience. There you are. All right, so let's say that instead of having this fancy craziness going on, we had sealed traits, my trait, and then type, T extends, this is my trait, type T extends my trait, right? And then underneath that, we're going to have something like, class, my class extends my trait, where we override type T, and we say that our override type T is going to be equal to my class dot type, or just my class. There we go. Okay. So what just happened here? And then let's say we had a function called def return me, and it returned something of type T. And it doesn't have to actually. And then we it doesn't have. We do not. Def return me, and this has def return me too, and it can return this. But what's the difference between these two return me's? The T up here, it could be a type of trait, right? But in the subclasses, when we override it, T, instead of being of type my trait, it becomes of the type that extends my trait. All right, what's the type that extends my trait? Oh my God, it's type my class. So this return me function goes from returning the superclass type to returning the concrete subclass type, the type of this. So what ends up happening is we get to keep the most specific type information possible and return that from our methods instead of, just returning, some generic interface, which allows us to call the more specific concrete methods in the subtype. And by combining this ability to return the most concrete possible subtype, along with the ability to pass in a type in the input parameter and get the most concrete type out, we can retain a lot of type information and do cool things with the type system. Such as what we were doing back here, right? Such as things like creating lists of different types, where you have a list that's of type like int concatenated to string concatenated to double. If you look at an example, let's test, there's a lot of boilerplate going on over here. But basically, let's say you wanted to have, we can, let's call this val list equals 1 concatenate to false, concatenate to high, concatenate to nil. Because the concatenate function can take in the type of the input and it can return the most specific type possible, and because we can use implicits for things like for implicit concatenators or whatever, we can keep the most specific possible type. So if you look at the type signature on this, what the type is the type is a list where the head is int, and then a list where the head is boolean, and then a list where the head is string, and then nil, right? So the types of each of these elements is stored in the type signature. So you can do cool things like, map all the ints to like the int doubled, or remove the first int, because all that type information is being held. It's not being lost to some interface. And we're not going to go into macros, but basically what macros do is there are multiple stages in Scala's compilation. A lot of the stuff that goes into Scala is sort of desugaring, and there's a lot of desugaring. There's a lot of layers of syntactic sugar in Scala. Java has less layers of syntactic sugar that the compiler has to deal with. So initially, the Scala compiler has to spend a lot of time sort of getting rid of desugaring, like getting rid of syntactic sugar. So if you looked at there we go. Sorry. If you looked at just you can get rid of this, ignore the compile error. But if you just look at what the compiler produced, you've got syntactic sugar for your initializers. You've got syntactic sugar for everything. For your this, you've got syntactic sugar for whenever you say like import, some long import statement, and then you use something that uses that import, it actually will expand that out. All of your implicits get expanded out. But basically, after a lot of this expanding happens, the types should all check, and that phase in the compilation cycle is called the typer phase. If you saw the previous thing, Shapely, that Shapely came from John Reed Lowell. This is my debugging library, Scala Trace Debug, but that thing came out of repositories, Shapely. It came out of this, Shapely, and the way you desugar it, you can use, this has a desugaring function, but what we used was -xprint typer, which prints the program tree after the typer compilation phase. So what macros do is after all the types have been checked, and after we've done some of this desugaring, before we get to more serious compilation stuff, what macros do is they allow us as the user to manipulate the tree of expressions, right? So you can think of a language as a tree of expressions. So like each line is like an expression. Or for example, if you had something like val result of type string equals val s1 equals hello, val s2 equals world, val s3, and then we're going to return s1 plus s2. This whole thing here is an expression tree of type string. This whole thing here is a tree. And then this is your branch, it's like your branch 1 of the tree. This is your branch 2 of the tree. And then the entire tree, after all these branches are taken care of, the entire tree is basically the same as just, right, that, and if we were to just get rid of the tree entirely, the entire tree would evaluate to just the last thing in the tree. So this and that are the same. They're both trees of type string. And what macros allow us to do is they allow us to take those trees and to manipulate them. We can add something to the tree, we can swap, replace, we can fabricate another tree, we can replace two trees that are the same type. So we can replace this, string expression. We can replace this with a different tree that also it returns a string. And so by doing that, they allow us to manipulate things, and even manipulate. Uh, One thing that they could be used for is like generating something that like a type that represents an integer, or turning types things into strings that aren't strings. And so a lot of crazy stuff, manipulation of Scala can be done with macros. And one really interesting way that that's done is with the not Shapely, not episode 1, with refined types. So with refined types, if we were to go to Scala refined types, one cool thing that refined types let us do is they let us encode something like whether the type is positive or negative into the type signature, and then use that to help us prove things without having to do without relying on runtime checks. So for example, one thing that I tried to do previously that didn't work out too well was I tried to, let's rename this into monitor. In our previous episode on functional style programming, we were doing mappings on monitors. Let's uncomment this and get to the very end. Uncomment this. Right, so we were doing a lot of, we had a monitor, it had pixels. The pixels had like a color. There was, a grid of pixels and a column of pixels. We could resize it by mapping. We could resize the grid and column of pixels by mapping. It was like a regular data structure. And one thing that we ended up having to do was this, verify that it's rectangular. Verify that the width is greater than 0 or the height is greater than 0, and things of that nature. And instead of doing that with runtime checks, we could do it with the compiler, with the type system, using this really cool thing called refined types. Yeah. And so you could, for example, play with that later. But basically, so you've got this really crazy type system that, there are crazier type systems. There are type systems that are built for proofs. Scala's type system is built, for useful things. Sorry, proof people. But yeah, there's a lot of crazy stuff that can be done that you couldn't do in Java, but that's still a production kind of a programming language. But yeah, so we covered, Scala type system. We covered a little tiny bit about macros. Could do a really quick, really fast little macro example from Shapely. So if we look at this code, we've got a macro. So this function from int, it's an implicit function, so it's an implicit conversion. So if the compiler sees an int and this is in scope, then it'll apply this function to create a nat. And this function is actually a macro where what this does, nat macros.materialize, it takes in a tree. The tree is actually a constant, an expr of type int, right? C dot, what is this? C.expr of type int. Yeah. And this is going to be int dot tree. Okay. So this int is going to correspond to that int. But this is actually it's actually an expression. It's an expression of type tree. It's not being type checked because the typer phase just finished, but the whole expression is like an int. And then this expression that is like an int, it's being matched, pattern matched, turned into a tree and pattern matched. And then we're saying, if it's greater than 0, call nest, the nest function on it, where the nest function will put this shapely.successor around it. And then it'll keep on wrapping. It'll do, shapely.successor, 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 shapely.successor until, until the tree, whatever, reaches 0. And then at the end, it'll have shapely.0. And what's going to end up coming out of this is something that's like, a type, something that's like a successor of 0. And this type, where shapely.successor is going to become a type, right? So if we were to look up successor, Control-Shift-F, successor, find 50, not .scala, case class successor. Here's successor, right? So what ends up happening with successor is, well, let's start with 0, right? 0 is a type, right? It's a type n, so 0.n is the type of 0, but 0 is something that represents 0. And then successor of, so for example, if we had successor of 0, we would get, successor where n0 is the type of 0. So we would end up getting something that's of type, of type successor of type successor of type, of something of like 0.type or whatever. And what that does is that type represents 0's successor. The type represents integer 2, right? So if we were to go navigate back. Sorry, my Control-Alt left doesn't work. Okay, this isn't working. But if we were to go back to, oh my God. Sorry. If we were to go back to here, what this does is this actually generates something of type successor 0. So if we pass in a number like 2, it'll generate successor.successor 0. And in the reverse case, if we say, if we say a type like, successor of successor of 0, the type itself will transform into integer 2. So we have this notion that types can be integers and integers can be types, and you can have, you can represent constraints like, something has to have a length of 4, or you can represent things like, something has to be positive or something has to be true or whatever. You can put these constraints into the type system instead of using your old-fashioned runtime checks. If something is true, continue, else, throw, exception, whatever. And some languages like Haskell to an extent, Idris are using features like these to create more robust code. Yeah, but now you should understand a little bit about macros. I use macros a lot in my library. So if you go to GitHub, John Reed Lowell, Scala Trace Debug, this is my library. It uses a lot of macros. But it'll use macros for things like, this is the most commonly used function, but it'll use macros for things like getting the line number, getting the file name, and then, concatenating them together to form Q triple question mark means generate a tree or generate an expression. So this whole thing generates an expression, and we're saying, oh, we're returning an expression of type string. So this function, apply, that returns a string, gets converted into a macro, pause impl, and this macro takes into context. The context is compiler context, whatever. And then it's going to, ask the compiler to get the line number and the file name, and it's going to generate this little expression. The expression is of type string, and it's going to substitute that expression in place of the call to pause.apply, or pause.apply is the same. Pause.apply something is the same thing as just pause that. In Scala, the apply kind of vanishes. The idea is that you can substitute objects with functions, so apply is like the middleman. But my library has a lot of macros, and so you can do something like log.warn and add a pause for position, or log.debug and add a pause for position. And what this does is it adds the package name, the class name, and the line number. And it does this in such a way that you can click on your print statements and it brings you to that location in the source code. A lot of people like me, a lot of times when I start to write a little program or a test program, I'm not going to go line by line with the debugger. I'll have a few print statements, and instead of doing like println and then look, oh, I forgot what line number I put the print statement, or control F, whatever, I just click on the print statement and then boom, I'm at the place, right? I'm pretty sure I already demonstrated this once before, but episode 1, right? Main. So if I were to do something like import, in Scala you can put import statements anywhere you want. Import scala.trace so there's debug. There's debug for Java methods. There's sdebug for Scala methods / macros. So for example, if you wanted to, print a desugared expression, that would be an sdebug. There is, we'll just worry about these two. So for example, if you did, actually let's start with pause, because that's the most used one, right? So dot pause for position. So if we did println hello world 1 and then println hello world 2 plus pause, and then we ran this, and let's say that we were in another file. Oops. That doesn't compile, does it? Probably messed up. Type list takes parameters. Yeah, so this doesn't, this would, let me see, match up to that, I think. Type T2. I think that'll, let's see if that compiles. I mess up syntax sometimes. There we go. And then this is not legal because of the way the types resolve. There we go. So if we were, say, in another file, and we wanted to get to the location of Hello World 2, we just click on it. Bam! We're at the location of Hello World 2. We could also click here to go down the stack trace, and it'll, boom, go to that location as well. And if your keyboard shortcuts work, you should also have keyboard shortcuts to jump to your print statements. So that's really nice. I sometimes use debug.trace instead of println just because you get this nice formatting. You get indentation and white space in between. So debug.trace, trace to standard error. Trace to standard error in thread main at scala.trace.debug. Oh. Whatever. In Java, you have to you have to specify an extra line of stack trace. So if you went debug.trace standard out 2 lines of stack trace 2, the first line of stack trace doesn't work. The second line of stack trace goes to line 9. I had to make the decision between having sort of 2 separate functions, one for Java and one for Scala, and I didn't want to do that. So the one for Scala has, java.main.line9 as the first row. The one for Java has it on the second. Sorry. But yeah, the Scala version works better. But all of this works in Scala as well as Java. Printing to standard error, printing to standard out, printing out arrays, printing out different kinds of containers. There's a compile time shutoff switch by setting the environmental variable, I'm not sure if I have it set, but there's an environmental variable, enable trace debug, right? If it's true, trace debug is enabled. If it's false, the macros can actually substitute the source code to get rid of it at compile time. Also, you can enable or disable trace debug, tracing to standard out, standard error at runtime as well. This enables or disables it for the debug.trace methods, not for the pause macro. For the pause macro, because it's just a macro, you can either have it in the source code or not. You have to use the compile switch. So yeah, there's debug.checks for runtime checks that will print a stack trace if the runtime check isn't fulfilled. There's debug.assert, which will terminate the program, forcing the person who wrote it to fix it, hopefully. If you want, you can use any of these methods. They all return strings that you can pass into a println or a logger or whatever. You can print containers of arbitrary length. So here we're printing out line 25. There is totally working. This documentation, I believe, is pretty up to date. It should, yeah. So you can check the documentation. Java doc should pop up. So if you're using something like debug.trace, traces the standard error with one line of text, stack trace to print whatever it is you want to print, returns a string containing what was printed or what would have been printed if printing was enabled. You can pass the string into a logger. Awesome documentation, right? You wish every single method had this kind of documentation. But yeah, you've got your documentation for sdebug, for debug, for log. Log is like pause, but instead of just giving you a position, you can put stuff in it. This is a tiny bit old. It doesn't have pause, but pause is really easy to use. It's just plus pause, right? Just plus pause. You have pause. Provides a file line position as a string to append to the end of a print or log statement. But yeah, you have documentation. There are implicit conversions if you want to, instead of typing in like debug.trace, you can just do .trace at the end and the implicit conversion will handle. So for example, if you added, let's say you wanted to do import scala.trace implicitly printable, and then you wanted to do something like hello dot println standard error. If the implicitly printable wasn't here, this wouldn't work, because what the implicit conversion does is it wraps this up. Implicitly printable, yeah. So it creates like a wrapper, I guess, if you want to call it that. But yeah, hello.println standard error, and what this should do is it'll print hello to standard error. One really nice thing about having it at the end instead of the beginning is if you do Control-Shift-R, you can find all instances of println standard error and replace it with nothing, and find and replace all files, and then boom, you got rid of all your print statements. Just one single control replace to get rid of all of them. So that's really convenient. Oops, nope, this is a different, yeah. You can print out containers. So here we're printing out a map 112233. It prints out the full type and then 112233. It's nice if you're doing like a little coding puzzle where you have like containers of integers or whatever, and you're doing it by print statements, and you want to print out the first 50 elements. This works for any Scala container. Trace contents. If you have something like foo.map ... bar map, what you could do is you could actually do the implicit conversion, and then you could actually add your print statements sort of in the middle of your chain of thingies. Like, so you could like, if you had something like foo map bar whatever, you can insert the print statements in the middle, and that'll sort of print each of the values in the middle. You can do the desugaring. So here, this expression 1 dot plus parentheses expression 2, expression 1 plus expression 2. This is like what the source code looks like if you were to do the -xprint typer command line option. It gives you an idea of what things are being desugared into. Sometimes if you have something there, it's like tons of foo whitespace bar whitespace baz whitespace, and you're trying to figure out what's going on with this domain specific language or whatever, you can get rid of the syntactic sugar and just understand what's going on. There's also trace code, which kind of doesn't do all the doesn't have all the dot parentheses stuffs in it. Trace code is mostly for printing variables. On occasion, you will run into, if you try to do like something fancy, it might not print correctly. I can't really control that. It came recently just added this. You'll find it in the source code, but basically on occasion I'll have like a really long print statement, and I'll want it to like format it, break on white space at 100 rows. If you have, if you use pause, you're using a macro, so there's no runtime overhead. If you're using dot trace, if you're tracing something that has a length of 0, so something like debug dot trace foo and then like num lines equals 0. This will make no call to generate a stack trace, so it's more efficient. If you want to, you can get rid of all of your stack traces and just make it regular print statements, just with something like Control-Shift-Replace, and then change this from 0 to 6 or 6 to 0. But yeah, I hope you learned a little bit about macros and the type system. Thank you.